In this video, we are going to be going over the prediction of products in substitution and elimination reactions, along with understanding how to draw them instead of regiospecificity and stereospecificity. And at the end, we will be going over some examples of all the different conversions that we can accomplish with certain alkyl halides. So, the first thing that we need to talk about when we're trying to predict the product in substitution and elimination reactions is how to actually find an effective way to identify what we have present in the reaction. And in order to do this, we can follow the analysis that is illustrated in this slide. First, we're going to determine the function of the reagent. Then we're going to analyze the substrate and determine the expected mechanism. And then lastly, we are going to consider any relevant regiochemical and stereochemical requirements for the particular reaction. So, when it comes to step one, understand that we have to find what is the function of the reagent that we are talking about. Remember, we need to identify if the reagent that we are using, meaning what is the nucleophile that we are bringing into the system, is it going to promote an SN1 reaction, an SN2 reaction, an E1 reaction, or an E2 reaction? Okay, so understand that when it comes to SN2, we are going to be looking at strong nucleophiles. In SN1s, we're going to be looking at weak nucleophiles. On E2, we're going to be looking at strong bases, and in E1 we're going to be looking at weak bases. In your textbook, as you can see, there is a summary of, depending on the type of reagent we have, is it going to be promoting SN1, SN2, E1, or E2. Let's go over the specific table that is illustrated in this slide. So when it comes to this, as you can see, if we have a particular reagent that happens to be, and I'm just going to highlight them as I talk about them, so if a particular reagent is a strong base, but it is a weak nucleophile, what is going to be promoting is an E2 reaction. Examples of this include sodium hydride, DBN, and even DBU. In the case that you have a strong base, and it is also a strong nucleophile like hydroxide, methoxide, ethoxide, those, depending on the reactant or starting material, will be promoting either SN2 or E2. In the case of reagents that are weak bases, but they're strong at the level of being nucleophilic, like iodide, bromide, chloride. Here we have a substituted sulfide. So these are going to be members. So these three in the bottom, these are derived from thiols. Okay. It could be protonated like in the last case, or they're going to be anions. They're all part of this group. And then lastly, we have, as you can see, hydrosulfuric acid, H2S. Those are going to be promoting either SN1 or SN2. Lastly, if we have something that it is a weak base and it's also a weak nucleophile, like water, methanol, ethanol, those type of reagents will be promoting SN1 and E1. Let's now go over the second step, which is the analysis of the substrate. Once you have determined what kind of mechanism will be favored by the reagent, then we're going to go back and analyze the substrate. So when we're talking about the substrate, and in this case, I'm focusing on the alkyl halides. Here, at this time, I'm just focusing on the alkyl halides. If you have a primary alkyl halide, as you can see, we need to now compare to the reagents. that we have. So if a primary alkyl halide, okay, is reacting with a strong base, that it is a weak nucleophile, then the preferred mechanism is going to be E2. If a primary alkyl halide is going to be reacting with a reagent that is a strong base and a strong nucleophile, as you can see, the SN2 is the preferred product. Some of the E2 product will also form. If you have a primary alkyl halide that it is reacting with a weak base that happens to be a strong nucleophile, as you can see, the preferred product is going to be SN2. Let's move on to the secondary alkyl halide. When we have a secondary alkyl halide, as you can see, if we have a strong base, weak nucleophile, we have the E2 product preferred. If we have a strong base, strong nucleophile, then the preferred product is going to be E2, and then in lesser amount, we're going to make the SN2. Lastly, when we have a weak base, strong nucleophile for that secondary alkyl halide, as you can see, the substitution, specifically SN2 product, is the one that is preferred. Notice that primary and secondary alkyl halides cannot react with weak bases, weak nucleophiles. Let's move on to the tertiary alkyl halides. When we have a tertiary alkyl halide, understand that if they are reacting with a strong base, weak nucleophile, the preferred product is E2. If we're reacting a tertiary alkyl halide with a strong base, strong nucleophile, then the preferred product is E2. Then if we have a tertiary alkyl halide with a weak base, strong nucleophile, understand that we're going to have the SN1 product. And lastly, if we have a weak base, weak nucleophile with a tertiary alkyl halide, we are going to form in equal amounts the SN1 product and the E1 product. On the step 3 of how to predict the products when we have substitutions and eliminations, remember that we also have to think about regioselectivity and stereoselectivity. So, regioselectivity refers to location in the molecule. Stereoselectivity refers to the particular stereochemistry in other words, the chirality that needs to be present in that product. So let's go over for each of them what is the regioselectivity and the stereoselectivity. So in the case of SN1 reactions, and again, these are substitutions, the nucleophile attacks the carbocation. And remember that in these, because the leaving group leaves, since we have the formation of a carbocation, understand that rearrangements can take place. So whenever you have an SN1 product, because of that carbocation, understand that you always have to be on the lookout for rearrangements. Now, when it comes to the stereoselectivity, remember that the nucleophile is going to be replacing the leaving group. So the main thing that you have to remember that since that nucleophile in an SN1 reaction can attack from the front of the carbocation or the back of the carbocation, we are going to be forming racemic mixtures. In the case of an SN2 reaction, remember that this is a concerted mechanism. The nucleophilic attack is going to happen at the alpha carbon, and then the leaving group is going to be leaving. So that's the location of where the reaction is going to happen. Then, when it comes to stereoselectivity, remember that in this case, the nucleophile is going to be replacing the leaving group. But because this is a concerted mechanism in the way that the mechanism proceeds, since that nucleophile is going to be attacking from the back of the molecule, the product of an SN2, if we are still having a product that is chiral, is going to have an inversion of configuration. When it comes to E1 mechanisms, understand that the CHEM221 product is the one that is going to be favored over the Hoffman product. Just to remind you, the CHEM221 rule states that the major product is the most substituted alkene, meaning the alkene that has the most carbons around the carbon-carbon double bond, okay? The Hoffman product is going to be the opposite. In an E1 mechanism, remember that this process is stereoselective, okay? When applicable, a trans disubstituted alkene will be favored over the cis. So when you have the formation of these products, remember cis and trans are possible, but trans is going to be in is going to be produced in a larger amount. When it comes to the E2 mechanism, remember in the E2 mechanism, it's a concerted process. It happens simultaneously. The base deprotonates the beta hydrogen in the system, the electrons that are in between the beta carbon and the beta hydrogen form the carbon-carbon double bond between the alpha carbon and the beta carbon, and then the leaving group leaves from the alpha carbon. So when it comes to the E2 mechanism, remember that the Cis-F product is generally favored over the Hoffman products unless we have a sterically hindered base, okay, in the reaction, which then the Hoffman product is the one that it is favored. Now, when it comes to the stereoselectivity for an E2 mechanism, remember that the process is stereoselective because when we can apply it, a trans disubstituted alkene will be favored in comparison to the cis. Now, the process is also stereospecific, okay? Because specifically when the beta position of the substrate has only one proton, the stereoisomeric alkenes result from an anti-periplanar elimination, okay? So what does that mean? In an anti-periplanar mode, if these are the carbons that are going to lead to the formation of that alkene, anti-periplanar means that that hydrogen and that halogen, which I highlighted in green, are going to be on opposite sides but in the same plane. That's what anti-periplanar means. Remember, since we're talking about an E2 mechanism, we're going to have the base, again, grab onto the hydrogen that is on the beta carbon, then the electrons between that beta carbon and that beta hydrogen are the ones that are going to be forming the carbon-carbon double bond between the alpha carbon and the beta carbon, and then the leaving group is going to be leaving. Understand that all of this is very important because one of the main goals of organic chemistry is to have synthetic strategies. And the synthetic strategies are the ones that are going to be giving us the ability to synthesize a whole bunch of different functional groups, okay? So understand that the variety of products comes from the different reactions that you guys have learned so far in the course, meaning first semester organic chemistry. Now, here I just want to zoom in and look at a particular set of reactions coming from a primary alkyl halide. As I discussed previously, in specifically primary alkyl halides, we can form a variety of functional groups. And here are illustrated in this roadmap that we have in the bottom. As you can see, alkyl halides, if you have a particular nucleophile, in this case sodium cyanide, we can form a nitrile, okay? If we have our alkyl halide and we reacted with, let me just start clockwise. If we have an alkyl halide and we reacted with, in this case specifically as acetate, we can form an ester. On the third reaction, this is where we have that NaSH, which is one of the nucleophiles or the reagents that we learned in the previous slides, that if you have a primary alkyl halide, this is going to be undergoing SN2 reaction and you form a thiol. If you have methoxide on this reaction number 4, as you can see, we can form an ether. If you have a primary alkyl halide, if you're using one of those weak bases, strong bases, weak nucleophiles or bulky nucleophiles, we can form an alkene. This is reaction number 5. If we are reacting that alkyl halide with sodium hydroxide, we can form an alcohol. If we are then taking this alcohol and then reacting it with HBr, we can reform that alkyl halide. And again, an alcohol can actually form an alkyl tosylate, and then that leads to the formation of an alkene. So this comes to demonstrate that the reactions that you have learned actually are interconnected, and then they can form a variety of functional groups. Let's look at reactions now for tertiary alkyl halides, okay? Understand that the reason why we go over this is that this is important because in second semester organic chemistry, since many of these reactions form specifically the starting materials of what we are going to be discussing, this is why you need to have all of these reactions under your belt. Because you will be utilizing them or proposing the synthesis of these reagents, because they are the reactants that we are dealing with in second semester. Now, when it comes to tertiary alkyl halides, as you can see, we have the formation of alkenes, okay, depending on which one you are proposing. So here, I'm not going to go over all of these in detail, but I suggest that when it comes to this, that you will look at the reactant, look at the reagent, and understand how those products are going to be produced. My suggestion is to make flashcards in order to remember these better. And again, the main thing is that these reactions are going to give rise to the starting materials that we are going to be discussing in second semester organic chemistry.